Okay, it's 7 o'clock. So let's go ahead and get started. I imagine we're going to have some other people pop in a little later, but that's okay. Let me move this out of the way. Before we get started with the meeting, wanted to mention something to you guys. I think I mentioned last meeting that on the schedule. Let me pull up the schedule here. I was planning on the Tuesday meeting on the 30th. We were going to delay over from Tuesday till Thursday because I was going to an astronomy event. And good news is that actually the event is being opened up to more people. So I was going to go ahead and tell you guys about it. It is something that's happening on Tuesday night and Wednesday night. So I know a lot of you guys are working, so you may not be able to attend, but let me go ahead and just mention what it is. It's a little, very small astronomy session or get together, camp out, whatever you want to call it, up by the, where's it at? The lakes area up past Payson, over in the Payson way. It's called the Hyman Ranch. This guy has 20 acres up there with his couple of his kids, and they wanted to invite up to 20 something people up there for 2 nights. It has a little gazebo type of thing and a bathroom in there. You'd have to bring your tent, and it's a Bortle 2 sky, means it's very nice and dark. So anyway, if anyone is interested in it, let me know by Thursday. Just email me and I can send you the more information about it. It's about an hour and 15 minutes from Payson. So you go to Payson, and then you head northeast to Payson. So Jeff, I assume you're working, right?
Yeah.
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 And
I'd have to take off, but yeah, I'm working.
yeah, and Frank, your back probably wouldn't allow you to go camping out there. So, but you're.
I don't know about that.
Oh, well, if you're interested in details, Frank, let me know. I'll be happy to.
I'm very interested.
Okay. I'll email this out to everybody. Let me know by Thursday morning because I'm going to send it out to the general evac club Thursday afternoon and open it up. Right now, he wants to keep it really small. This is the first time he's ever done this. And if it works out well, he maybe do a bigger thing. There's no cost involved with it. It's just going up there. It is on a dirt road, but the dirt's in good shape. So any car can make it. You just have to go a little slower. It's 7 miles on the dirt road. And it's up past Payson. So I'll send this out to everybody. And we're also thinking about doing a potluck. So once we get everyone figured out who's going to participate, we'll go from there. Okay. Any questions on? Yep. Any questions on this before we move on?
Looks like fun.
Yeah, I'm looking forward to it. I'm going to be up there. It's going to be nice and high up there. It's 7,400 feet, so temperatures are pretty cold at night and nice during the daytime. So. Sid, I'm glad you're able to join us there.
Hi.
Hey, Sid. Let's go ahead and get started. Is this big enough for everybody to see the text on the screen?
Yes.
Yes.
Okay. So,
quick question. Can I ask you something real quick? It's kind of, what is the best software for an iPad for scanning the sky? I don't care if it costs money. I want the best one. I've tried a couple and they haven't worked out.
I think I've pointed out the same one to you a number of times, but maybe it didn't work out for you. Sky Safari is my favorite.
Okay. I haven't tried that one.
That comes in 3 different flavors. Let me pull it up here. Find
it's on there, in there. Oh,
well, it's on my iPad, but I can get you the website where you can get more information on it.
Okay.
Sky Safari. Here it is. So there's 3 different flavors, and you can also get a subscription base. So the basic is on sale for $2.99, was normally $5. The Plus is $12.99, normally $20, and the Pro is $36, normally $50. The nice thing about the Pro is it supports a number of different mounts. It also lets you make your own observation list and store that on there. So that's kind of cool. And but what is nice about the subscription one, I can't remember how much that costs. It's Pro plus a monthly fee. You can actually do stuff on the computer, and then it'll automatically sync up with your iPhone and stuff. So anyway, this is what I use, and it's probably by far the most popular software that most astronomers use. So
Thank you.
no problem. All right, so tonight, this is probably the hardest part of the classes, the night sky. We're going to cover a lot of concepts and everything, so please feel free to stop me if I lose you or something. So let's talk about some of these terms. Obviously, we're going to go into much greater details on what each of these terms mean through the chapter. The altitude is when you're looking at one of the coordinate systems on determining where things are at. Altitude is the height up in the sky it is, and that goes from negative on the horizontal system, and it's divided into degrees and minutes and seconds, and it goes from negative 90 to plus 90, with 0 being directly overhead. The azimuth is the coordinate system, same coordinate system as the altitude, but it's basically the compass values. So it ranges from 0 to 360. So between these two things, you can specify where something's at in the sky. And again, we'll talk about that in more details later. The Bortle scale, which I just mentioned, is a 9-level numeric scale that measures the night sky's brightness in a particular location. And the way it goes is if it's very bright there, which is bad, it would be a high number, like number 9. We live in the Chandler area is a Bortle 8. A Bortle 2 sky is very dark. I don't know that there's any Bortle 1 sky. There probably are, but I don't know where that would be at. So probably Antarctica or something. Celestial coordinates. That's a grid system that is used to locate things in the sky, much like the alt-az system, except the alt-az system is a relative system where the celestial coordinates is an absolute system. So the celestial coordinate is kind of equivalent to the longitude and latitude on Earth. It doesn't make any difference where you're at when you get a longitude, latitude coordinates. You know exactly where that other person is at on the Earth. We'll talk about that in much detail later on. Celestial sphere is basically a concept of where you take the stars in the sky and project them on a sphere, and that's where you get the celestial coordinates at, essentially. Circumpolar basically just means that it never sets. So if a star is called a circumpolar star, that means the star actually never sets, and that's because it's close to the north celestial pole. What is circumpolar may change depending on what latitude you are, and we'll talk about that a little later on. The constellation is a distinct pattern of stars defined in the sky. It also represents an area of the sky, and there's a total of 88 official constellations defined. The declination is part of the celestial coordinate system, the equatorial coordinate system, and that is just the height above the sky, basically, and that goes from above the ground from minus 90 to plus 90. Again, the equatorial system is a second system used to identify something in the sky, and it's absolute coordinate system. The horizontal coordinate system we were just talking about, that's the alt-azimuth system, and that also defines where something is in the sky at a particular place and a particular time. It's a relative coordinate system. Magnitude is how bright a star is in the sky. We'll talk about that also later on. And the north celestial pole is the point in the sky where it appears that everything else rotates around, and that's very close to the Polaris. Right ascension is the other coordinate that's used in the equatorial coordinate system. It's right ascension and declination in that system. We'll talk about that later on. And surface brightness, we're going to talk about later on also. It's basically how much light is in an object for that particular area of that object. Okay, I know there's a lot of terms. We'll get into more details on those later, but did I confuse anyone really bad on any of the terms so far?
No.
Okay, let's go on. The sphere of the sky. The Earth spins like the top of the North Pole, roughly aligned to the North Star. In this demonstration, or this little exhibit here, you can see the North Pole's here. Some guys standing on the Earth there, and the Earth rotates around that axis. So zenith for this person is directly overhead. That's what zenith is. And the Earth's equator projected out becomes the celestial equator if you would project that out. And a good example of what it looks like as far as this or demonstration of how the Earth is rotating is if you were to just take your camera and put it down facing north and take multiple time exposures, you'd get something like this here. So I took this on one night when I hiked up to Weaver's Needle overlook area. Picture there. Okay, so let's talk about the coordinate systems. As I mentioned earlier, there's two primary coordinate systems in astronomy. The equatorial system uses the right ascension and the declination to identify objects in the sky. The right ascension are units, the same as the units as a clock. That's hours from 0 to 24, minutes 0 to 60, and seconds ranging from 0 to 60. The declination utilizes degrees ranging from plus or minus 90. So let's take a look at what that looks like. Here's the equatorial system. As you can see, this sphere of the sky is divided up into 24 segments, going 22, 0, 20, or 2 hours, and so forth around. And then the declination goes from the very North Star, which would be plus 90, down to the very South pole, which would be minus 90. Now, obviously, we here in our area can't see as far as minus 90. I think we can go down to about negative 30 and is our horizon or somewhere around there. Is that kind of a good sketch of the equatorial system for you guys? Sid, are you okay with this so far?
Yeah, but I just have a question.
Sure.
Why do they call it hours?
Yeah, I think, I'm not sure the historical reason, but I think the reason might be to do with the Earth rotates completely in one day. That's 24 hours. So they just break it up according to that. And that's why you guys may have never seen this before, but initially, or 30 years ago, before they had some real good telescopes, they would have what's called clock drives. And it would just, once you get north aligned, it would just follow that just like a clock. And that's why they call it clock drive. It would just rotate like a clock. So it's a good question, Sid. And I think that's the reason why. So as you can see, if you specify a location here on the sphere and say, let's say it's 20 hours and plus 80 degrees, you can see exactly where that is on the sphere. Now, the other system is the horizontal system, also known as the alt-az system. This is a relative system, so it really depends on where the observer is at and what time the observer is looking. So, for instance, if I were to tell you Jupiter is, or let's say it says a star here. So let's say a Taurus is at this location. You can give the altitude and the azimuth readings for that, but that's only those values are only good for that person. And if you wait an hour later, it'll be at a different location because remember the star is rising or setting. So this is a relative system, and it's not really that great of a system. But the reason why it's still around is because a lot of the go-to telescopes now have alt-az mounts on them. So that's this system that they're using. Now they can still follow stuff, giving coordinates in the celestial equator, but it's really going horizontal and vertical is what it's doing. So you may not use it, but the telescope's using it, doing calculations in the background using it if you have an alt-az mount, go-to mount. Okay, any questions so far? Okay, so I wanted to go ahead and give an example of how this works relative to, like, if you're on Earth, what would be the equivalent? So for instance, in Earth, you're given longitude and latitude values. You know exactly where something's at. No matter where you are on Earth, you'll know where that location is. That's kind of equivalent to the equatorial system. Where if you're at a location, you want to know where this other location is relative to you, that would be a bearing and elevation. As you move, that bearing and elevation moves also. That would be the equivalent to the alt-az system. So those are just two examples of a relative and absolute systems. Okay, so that's the discussion on the different coordinate systems. Is there any questions on that before we move on? Okay. So let's talk about the constellations and the seasons. Well, as you guys know, you can see in this diagram here, as the seasons go by, as the year passes through, the Earth goes around the sun. And as the Earth is orbiting around the sun, what is visible in the night sky, that would be back here, changes because, if the Earth's over here in August, over here it might be in a different area in, let's say, December, you'll see these constellations over here. So that's why you've got constellations that change throughout the year. The night sky views change throughout the year as Earth is orbiting around the sun. The star chart, if you guys have you guys ever used the star chart? Frank, I think you've used star chart before, right? Sid, do you know what a star chart is,
Yeah.
Sid?
I've
Okay.
used one of them before.
Okay, and how about you, Jeff? Have you used them before?
Yes. Yeah.
Okay. Yeah, so you just dial in what you are, and it'll show you what's in the sky at that point in time. So let's talk about magnitudes. So visual apparent magnitude. It's another system developed by astronomers to express how bright something is in the sky. Now, this is taking the total brightness of that object. So for instance, you can see the sun, and it's kind of not a very intuitive system. First, it's logarithmic. So a change in magnitude is what we call it, just like earthquakes. Changes from magnitude 5 to 6, let's say, is a 2.5 times difference change. So that's the first thing that's not very intuitive. The second thing is it seems like it's kind of reversed, because the very bright things are negative and the very dim things go in the positive direction. So here you can see the sun is a negative, I don't know, 27 or 30 magnitude, while the moon is a negative 12, it looks like. Venus could be as bright as -4. Vega is at 0. And then you get the dimmer stars, or the other stars coming in over here to the right more.
Wait,
So,
what? Oh, sorry.
No, go ahead, Sid.
What's a quasar?
A quasar? That's a good question. It's been a long time since I looked at it. I think it's a star that's ejected. It might be a galaxy, actually. I'd have to look that up, Sid. I think it's a galaxy that's very, very far away in the very beginning of the universe type of thing. I believe it's a really bright galaxy. We'd have to look that one up there. So they're very, very distant, though, I can tell you that. So anyway, that's the apparent magnitude scale. Any questions on that? Okay, let's talk about light pollution. So here's a map of the Phoenix metro area, and it's showing you how bad the light pollution is. Obviously, the blue and the gray are darker areas. But what scientists want is a way to explain exactly how dark a sky is, and that's where they came up with the Bortle scale. So the Bortle scale is a way of measuring how dark the sky is directly overhead, and those values range from, as I said earlier, a Bortle 1 up to a Bortle 9. So here's a chart down here that shows a Bortle 1 star. You might be able to see, if you have excellent eyesight and it's directly overhead, you might be able to see as far as dim stars down to magnitude 7.6. Bortle 2, and so forth. We're in a Bortle 8 sky. So what that means is all the stars that are less than 4.5 in magnitude are washed out by the sky background. So, and typically, in most cases, in a dark sky, you can see about 6 magnitude star between 6.1 and 6.5 in a dark area. You can typically see that. But here in the Phoenix metro area, you can only see down to 4.5 magnitude. Okay, so let's talk about another thing that's related to Bortle scale and magnitude. Actually, this ties the two together. So the magnitude is how bright something is, and that's the total amount of light coming from it. But there's some objects, well, for instance, stars are just points of light. So magnitude is a good measurement of how bright they are. But if you're looking at something like a nebula, it's actually spread out over a distance. And so when you're given a magnitude of a nebula or globular cluster or something like that, anything that has surface area to it, that's the total amount of light coming from it. So the object can still appear very dim, even though it may seem like it should be fairly bright, like a magnitude 7 or something, but if it's spread out over a big area, it may actually be almost invisible to you because that light is spread out over a big area. So that's the concept of what surface brightness is. So let's go ahead and do a visual representation of what we're talking about. So for instance, here on the right-hand side, these two guys, so this gray box here and this white box here actually are the same magnitude. They have the same amount of light that's coming from them, except for this smaller one is more concentrated. So it appears brighter. Well, because it is brighter, right? But the amount of electrons coming from this gray total the number of electrons coming from the white. So it's much easier to see this contrast between the two. Okay, so that's surface brightness. Now let's add in light pollution. So this is where the Bortle scale comes in. So in this example here, you can see this is a fairly dark sky off to the left here. And, oh, I'm sorry. These are both the same, represent light polluted sky here as opposed to a very dark sky. So these are the same squares. The inner squares are the same, but the outer squares are different, representing light pollution. So as you can see, it's harder to distinguish this square here from the background, although this is the same brightness as this square off to the left. Now you notice also that it really doesn't seem to make that much difference with this one on the right. It's still very bright relative to the background. And that's why when you're in the city, you're not really impacted as far as what you can see for multiple star systems, the moon, and planets. They're so bright relative to the background that the background really doesn't make any difference. On the other hand, if you're looking at a globular cluster or a nebula or something like that, it's much dimmer, so it's harder to see that contrast between the background and the object. So this kind of just brings all those concepts together. Any questions on that? Frank?
Sorry.
Go ahead, Sid.
Would the one that's like the more concentrated, would that be like a planet?
Yeah, it could be a planet because it's very bright. It still has, usually the planets do have some surface area, but they're very, very bright. Stars, planets, those are good examples of this, what this would be like. Jeff, did you have a question? You're on mute, Jeff.
There you go. Okay. Yeah, you said something about like dark sky objects, so that would be more of like that other one.
Deep sky objects. I may have said dark sky, but I meant deep sky objects.
Yeah.
So deep sky objects would be galaxies, globular clusters, anything that's outside of our solar system is basically a deep sky object. Right. Frank, did you have it? Oh, go ahead, Jeff.
I was going to say, as far as representative of that light pollution, would that be the dimmer one?
Yeah. So over here on the left-hand side, this gray square inside the other gray square, this would
Yeah.
represent like nebula or galaxy or something like that in our light polluted area.
Oh,
Where
okay.
this one on the right, this would represent a star or a planet or something like that in our light polluted area. As you can see, even though this is in light polluted versus this one over here that is not, you can still see it plenty easy. There's no problem. That's because it's all concentrated in one area. Where these ones that are distributed out further, you can see the contrast. And this is really what it's about. Being able to identify a deep sky object is all about getting contrast in there. So the contrast is easier to see here as opposed to where there's light pollution. Frank, did you have any questions you wanted to ask about this so far?
No, you're doing good.
Okay. All right. Well, we're going to move on unless there's any questions.
As I've said before, it's like drinking water from a fire hose.
All right. Let's talk about different catalogs. So, we've got all these objects in the skies, and obviously, as telescopes were first made, people like Galileo and Messier and Halley started seeing all this stuff in the sky. So they started trying to catalog what they were seeing. The first one to actually do that was this guy called Messier. He was a comet hunter. And so what he noticed was that comets, as you see them night to night to night, they actually move through the sky. You guys probably know that already. They'll move relative to the background stars and everything. And so that's the way you identify a comet over a period of, let's say, a week or something. You can see the comets moving. So what he wanted to do was he started, he saw other fuzzy spots in his telescope, and he didn't know if they were comets or not. So rather than trying to figure out if it was a comet or not and forgetting about it and coming back to it and finding out that it wasn't a comet, he went ahead and started cataloging these objects that didn't move so he would know these aren't comets. I don't need to worry about it. And he came up with a list of 103 astronomical objects, and those are called the Messier objects because those are his list. Go ahead, Sid.
I thought there were 110. Didn't they add 7?
Yeah, they could have. I think this is what he initially came up with. So the number is kind of fudgeable. Sometimes I think I've heard 107, 105, and 110. So yeah, it all depends on who you're talking to. So that was an example of the first list that came up. And obviously, as telescopes got more powerful, we were able to see dimmer themes. And then on top of that, photography came into it, and that really changed things. And so you got all these different catalogs of different objects. Now, Messier, the range of what type of objects are in here is every type of object. There's globulars, there's galaxies, because they are all just fuzzy spots, a nebula and so forth. The new general catalog is kind of the same thing. It has all different types of objects in it. It's a list of 7,840 objects. The index catalog of nebulae and clusters of stars, this is mostly focused on open clusters and star clusters and stuff like that. And it has a number of objects in it. So you can see there's some catalogs. Here's another example. The principal galaxy catalog is focused mostly on purely galaxies. That's all they're interested in that. Here's a catalog for dark nebula and so forth. So there's a whole bunch of different catalogs out there. These are some of the more popular ones. But the ones you'll probably be messing with most is the Messier object and probably NGC. And I forgot to mention, the Messier object is usually referenced M. So if you had M101, that would be Messier 101, where NGC references the new general catalog and it has a number associated with it. Now, what's kind of interesting is a lot of times the same object will be in multiple lists. So for instance, the Andromeda Galaxy here is known as catalog numbers M31 for Messier. It's also NGC 244. And here's, there's all these catalogs with different and unique names given to the same thing, the Andromeda Galaxy. So don't be confused by that. I realize that the same object may have different numbers. Questions on any of those stuff so far? Okay, moving on. Multiple star systems. So we're covering a lot of topics. let's talk about multiple star systems, how they work. So again, I've been kind of more interested in the multiple star systems as of late because I'm stuck in the city. And so what I can look at in the deep sky is very limited. I can photograph anything in the deep sky I want, but looking at things is very limited. Multiple star systems are one thing that does not, you are not limited in the city. And there's a lot of multiple star systems. So let's talk a little bit about what they are and the system used to describe them. So what are these multiple star systems? Let's say if you took Jupiter and increased its size by 10 times, it would turn into a sun. And so we would then be in a binary star system. Those are two suns in the same solar system. So that's what a multiple star system is. And oddly enough, they have discovered that there are some that have as many as 7 stars in the same solar system. It's beyond me how that's possible, but apparently there are some like that. Now we can't see those. You know, they are saying here about 85% of stars are actually multiple star systems. You can't see those normally because they're so close and we're so far away. They just appear as one stars. So how can they figure out, you know, even with the most strongest telescopes, they can't visually identify the 2 stars. How do they know that there are 2 stars in the system? This isn't actually in here, but I think it's kind of interesting. So what they do is, this goes back to chemistry. Each star has its own spectra that is associated with it. And what they have identified is if those 2 stars are orbiting each other, remember Einstein's Doppler effect where the wavelengths will change, they'll see the spectra going, being shifted when it's going away from us in the orbit versus when it's coming to us. So they'll see 2 separate spectra that are shifts over time. And they say, oh, that's a binary star system. So very interesting how they figure that stuff out. So multiple star systems, and there are some beautiful ones. This is probably the prettiest one in the night sky out. I probably butcher it. It's in Cygnus. It's called Alderigo. It's not pronounced like that. Anyway, that's a real nice one. That's in the Summer Triangle. And that will be coming up later on. I don't know if we're going to be able to see it in our class. Anyway, there's some like the Epsilon Lyra. That's the actual 4-star system that a good telescope can usually identify. And there's 2 stars here and 2 stars over here, and they're orbiting each other. This 4-star system. These other stars are just background stars. So how do you specify? Oh, go ahead, Sid.
Do you need like a good dark skies to see the ellipse in Lyra?
No, you do not. So that's a nice thing. These star systems, all you need is a good telescope to be able to see, you know, depending on how close they are, the bigger the aperture, and I guess we'll get into that in a little bit, the bigger the aperture of the telescope, the smaller distance you can see, provided you have good optics. Optics are really important, and collimation on your telescope is really important for this kind of thing, because if you don't have good collimation, you're not going to get points of light. You'll get a more fuzzy things, and that'll spread it out more. So 2 objects that are close together are going to look more like one object. Okay.
Thank you.
Yep, no problem. So how do you describe these systems? So the scientists have come up with a way to describe them. And so there's 2 principal values they use to describe a system. And that's the relative position here in this center here. Let me increase the size. The relative position of the secondary star, that's usually the dimmer star, to the brighter star here. And they just take it on a compass value. And it seems like it's backwards to me. They go 60 this way, 90, 180, 270, and 360. So anyway, that's how they tell you the location relative to it. And then there's a distance, you know, how far this one is from that one. So between those, this is a lot like alt-azimuth, actually. As long as it tells you what the degrees is and then the distance, you'll be able to identify where these stars are. So that's a system that we use to identify or describe what the system is like. And honestly, I don't pay it too much attention. What is important in this, the relative position, you know, degrees wise, because when you're viewing it through a telescope, you could have a right angle in there or whatever other pieces in there that might flip the relative location of those stars. The distance, though, that's really what's important, because how far these are apart from each other is going to be determine whether you're going to be able to see it in your telescope or not. But it's good to know this other information too, and realize what it is. Position, angle, and separation are what these two things are called. So here's a pretty interesting little table. If you have your optics are in good condition, and got a good eyepiece and everything, this table will tell you how dim. Let me see. There's two things that it's going to tell you, or that you need to consider before you can see if you're going to be able to distinguish the two stars. One is the distance the two stars are away from each other, because if they're so tight, you might not be able to resolve the space in between them. The other is how bright they are to each other. So, for instance, if you have a really, really bright star over here and a really dim star over here, the bright one can outshine the dim one and actually kind of consume it in its light. And so that's where this is the magnitude difference between the two stars on this columns over here, or rows over here. And then the columns represent how big your telescope is. And then it'll tell you how far down, how close two stars can be before you can't distinguish them anymore. So for instance, let's take 150 millimeters, that's a 6-inch telescope. And let's say the stars are about the same brightness. If they're the same brightness, you should be able to see stars that are as close as 8 arc seconds together. Yeah, 8 arc seconds together. On the other hand, if there's a really big difference in magnitude, a 4 times magnitude in difference. Now 4 times I think that's 100 times the difference in brightness. We'd have to look at the chart to be sure. 4 times magnitude. Well, you can only distinguish up to 2 arc seconds apart from each other. So you can see it's always already doubled the distance before you'll be able to distinguish them. So that's how that table works. In reality, you'll just start getting a feel for it once you start looking at some double star systems. Any questions on the double star system stuff? Okay, moving on. Star charts and atlases. These aren't used too much, obviously, these days, but it's a good thing to know how to use them. And also, your software in your iPad and stuff really has the same stuff in here. It may not be apparent, but it's still there. So how can you read these charts? Here's an example of a chart over here on the right. Make this nice and big. And you can see on the right, on the top up here, you have the hour. This is the right ascension value up here, 10 hours, 11 hours, 12 hours, and so forth. And you can see it goes down there. 12 hours is over here and goes down. And over here on the right-hand side, you have the declination values, 18 hours, 19 hours, 20, I'm sorry, here, 70 degrees, 60 degrees, and so forth, right? So here's the declination along these lines, and the right ascension is along these lines here. Okay, so that's that. The third thing that we're pointing out here is the star name. On these charts, they'll usually give the name of the star. And if you look here, it says, this is Polaris here. You can see that line, that star has a little line through it. And for this particular one and many different atlases, the line through it means it's a double star system or multiple star system. And as we know, Polaris is. Another component of them is the constellation areas or boundaries. That's the dotted line that goes across here. This is the boundary for Cassiopeia. And then there's number 5. They'll a lot of times it gives the Greek alphabet associated with the star. So the way and there are exceptions, but basically most stars, if in addition to their common name, if they have one, when they're in the constellation, they give them the brightest star in the constellation is Alpha. The next brightest star would be Beta, Gamma, Delta, and it goes down the Greek alphabet. So that's what this represents. This is Gamma. What is the constellation? I'm not sure what constellation this is. We can drop down to Cassiopeia. You can see right above where it says the S's are in Cassiopeia. There's a star right above that. That's a double star because it has a line through it, and it's Psi Cassiopeia is what you call it. Okay, now in addition to that, this star is also has other catalog numbers. You know, it has a SAO number and probably half a dozen other numbers associated with it. But you know, this is how it's identified for the most people in the is given the Greek alphabet of it. If it's not big enough to have its own name, you know, the large ones are going to have names associated, like Polaris has a name, but it's also Alpha. Polaris is also Alpha Ursa Minor or Little Dipper. Okay, what else we got? Talked about all those. So what if we want to find out what the right ascension and declination of something is? So let's say this object down here is M103. This looks, let me zoom in on it a little better. And down. So if we're trying to find 103, what the coordinates of that is, you can see here, the symbol for it is an open cluster. So it's an open cluster. And if we look at the hours down here, it's at 1 hour, and we got to approximate, there's 1, 2, 3, 4, 5, 6. So each of these is 10 minutes, 1 hour and 20, 30, let's say 32 minutes. So it's 1 hour and 32 minutes for the right ascension. And then the declination is over here. It's above the 60. Here's 70 up here. And it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 tick marks. So it would be 60, probably 63 degrees would be the declination. And so the actual values are given here. So that's how you would read it using a star chart. Obviously, it'd be better on the computer program, but that's the idea of how you get the right ascension declination using the chart. Any questions on this? I don't know how relevant this is anymore these days because everyone's using their devices. Okay, so let's put it all together. So let's say we want to look at a star, Mizar, which is the second star in the Big Dipper, located in Ursa Major. We can use a star atlas or online application. We can see its right ascension and declination here at the right ascension. So let me take Mizar in the software here. You can see Mizar is here. And if you click on it, it'll show you the name, what the magnitude is. Separation, it's a double star system, so it's showing the separation. It's 8 arc seconds, and the angle is 214 degrees. It also shows the right ascension and the declination. Here, the right ascension is 13 hours. Let's see if we can find the hours. Here's 13 hours, 20 minutes. Here's the line for 13 hours, 20 minutes, and it's down below that. And then here's the 55-degree line, and we can see it's before that, so it would be 54 something, right? So, and coming over here on the chart, same thing. You can see the hours and the right ascension and the declination, and here's the star and constellation it's in. And you can access online applications. There's, which one is this? Stellarium. This is a piece of freeware. Just load it and view it through your browser here. You know, set your position and click on, let's say, Capella. And there's the information about Capella, where it's at, and all that other good stuff. So this is a pretty nice little piece of software that you can use. Okay, that covers most of the material here for tonight. We've got references and resources, and then we'll go through the lab. Before we go in the references and resources, any questions on anything we covered so far?
No.
I know it's a lot of material, and it's not much for the observation stuff, but it's all good information. Okay. So some references. If you're interested in double star system, East Valley Astronomy Club has a double star program where you can go through actually multiple stars. Go here and it'll give you a list of multiple stars. So if you're looking to do that, look at multiple stars in your backyard or something. This is a good place to start. You can, find some popular ones here. I think it's 100 stars that it'll list or so. And these should be mostly visible in our areas. I did notice that some of these stars are very low on the horizon as far as down south. So I don't know that all of them are viewable, but a good percentage of them should be. As you can see on the names here on the left-hand side, Lambda Orionis. Well, what does that mean? It's Alpha, Beta, Gamma, Delta, Lambda. It's like the fifth. I'm not sure if that's the right sequence of the Greek alphabet, but anyway, that tells you, which star it is in that constellation. All right, so that's that. Then there's also the Royal Astronomical Society has a double star program. We also looked at the Stellarium Web already. Sky Safari was what we were talking about at the beginning of the class, right? That application you can download on your iPad. The Live Sky. This is kind of interesting little website. It highlights what might be of interest for tonight. So it's showing the different things that might be of interest to you guys for the night. I think the bigger it is, the more people have been querying about it. So planets visible tonight. This is kind of a cool one, although there's basically no planets, unfortunately, visible for us. But anyway, this is a kind of a nice little thing that shows what the planets are, how big they are relative to each other, when they rise, when they set, and all that other good stuff. It's a nice little website. Constellation guide. This tells you all about the different constellations. And then objects in the constellation. Light pollution map. If you're going somewhere or want to know what your area, how dark of sky you've got, this map will help you out. Identify where to go if you want to go to dark skies or how dark the sky is where you're at. Let's see. The Adeline has joined us. Welcome, Adeline.
Hello, James.
The Bortle scale. This is an explanation of the Bortle scale that we discussed earlier. So it tells you all about the different darknesses and what you expect to see, and gives examples of what Bortle scale looks like. There we go. Here's 8, 9. This is so kind of interesting. This is an excellent dark sky, good dark sky, and it goes out. And then we're at 8 and 9. And not really much visible there. It actually looks like you can't see anything. It's not that bad, but it's not good. And then you can actually, there's information on how you can rate your sky, but we've got all those other resources. So you really don't necessarily need that.
I have a question.
Sure.
So when you went to that Bortle scale website,
yeah,
didn't you say that there was we're going to some place that has Bortle 2? Can you actually see that, what it shows?
Yeah, here's Bortle 2. It's almost as dark as you can get. Bortle 1 is darker. So Bortle 2 is pretty good. You're probably not going to be able to do better than that. So. Does that explain for you, Sid, there?
Oh, yeah, thank you.
Yeah. Rotating Sky Explorer. This is just a demonstration on the rotation, how the sky rotates and everything. It's just a cute little demonstration. Let me see if I can show it. Now you can put yourself on here and start an animation, and it'll show the sky rotating and the stars if you want to show them. Big Dipper. So here's what the Big Dipper would look like as it's going through the sky, as the night goes on. So just kind of a good demonstration on how the Earth is rotating. There's an interactive sky chart. It's pretty much just one of those sky wheels, essentially, is what this is. And you put in the date, hour, time, and it'll show you the constellation. It's very basic, but it's kind of nice. You know, basic is good sometimes. Surface detail versus magnitude. We already talked about that. That's where a lot of this information on the magnitude and surface brightness that we discussed earlier comes from. And then free charts is just where you can print out some charts if you wanted to. So those are the references and resources for that. Any questions on anything we've covered so far in this chapter? Okay, so that's that. Let's move on to the lab that we're going to be having Saturday. Oh, and talking about labs, well, I got you guys here. So the parking was pretty bad. I guess Jeff is the only one that's here that was at the lab. The parking was pretty bad that night, and it's actually not very dark at 7:30. So I was thinking about kicking lab back to 11 o'clock. The parking should be easy, or I'm sorry, did I say 8 o'clock? To 8 o'clock p.m. rather than 7:30. I think that the parking will be easier, and the sky should be about perfect for, still be bright enough to set up, but getting dark enough by the time you're set up. The stars should be out and everything. Is that okay with you guys?
Yeah, you said 8?
8 o'clock, yeah.
Works for me.
Okay.
Sid,
Yeah.
you're good with that? Okay, I'll
Yeah.
send an email to remind everybody just so they don't get confused, and also update the website. So we'll do the labs 8 o'clock. Let's go into the lab material. Oops. There. So lab 2 is going to be about the moon. Let's see where the moon's going to be at. Actually, let's pull up Stellarium. Do I still have Stellarium up? Let's find it. I don't have Stellarium up. Let's pull it up real quick. If I can remember how to set the date on there, we'll see what's up. Operate off, move that. Let's see, here's the date. Okay. So let's back to real time. We'll set this up for, let's see, our lab is going to be on the 18th. 18 at 8 o'clock, just about. That's close enough. So let's see where the moon's going to be at.
Wait, when did you say the lab was?
Will be 8 o'clock.
Like
8.
what date?
The date is going to be the 18th. Is our next lab. Saturday the 18th at 8 o'clock. Right?
This Saturday, right?
Right.
Okay. Thank you.
Yep. So here's the moon. It's still going to be pretty high in the sky here. Looks like its altitude is going to be 48 degrees, so it's going to be nice and high. As you can see, it's not quite a full moon, which is good. We're going to focus, and I'll go back to the lab. We're going to focus, a lot of the interesting stuff when you're looking at the moon is along this dark and light area called the terminator. That's where there's really nice shadows to look at. So let's go to the lab. So here's some various terms that they use to describe features on the moon, or about the moon itself. There's the topology, basin, craters, escarpment, and so forth. I'll let you guys look at those in more detail later on. So when I'm thinking about looking at the moon, you can just go out there and take a look, or you can try to find some stuff that's a little interesting beforehand. So a good resource for looking at the moon and for planning stuff is this Liviation 2040 or 2024. And you can put in here the date and time, just like we did for Stellarium. And it'll show you what the moon is going to look like. So that's kind of a nice little scene. There it goes, just updated. Back here. You can also, there's a really good application that you get for the iPad or iOS device called the Moon Globe HD. And unfortunately, I can't show you what it looks like right now, but that's a nice application. It only costs $1. You can also download a PDF map of the moon. This is from the Geological Society, I believe, the U.S. Geological Society. Up here. And it'll show you a number of the features of the moon and everything. You can zoom in on it and see different stuff. So these are the tools that are nice for planning an observation session if you want to do that. So for our session, let me scroll past this real quick and we'll look at the diagram. We're going to look at these different areas of the moon. This is probably the easiest one to go to, Copernicus. It's going to be the most distinct crater in the moon, so it's easy to identify. The other thing I need to point out to you guys, depending on your optical train, the image might be reversed, flipped over or something like that, you know, if you have a right angle in there and stuff like that. So make sure you understand how things look through your telescope versus what's shown on the image here, because this could be backwards for you. So these are the objects we're going to look at. We'll look at Copernicus. Here's a little information about it here. Mare Humeron, Sea of Moisture. It's a big basin, 425 meters across, and it's a sea. Then there's this other object. I'm not even going to try to pronounce it. It's a Rima, and it's an interesting series of craters or fissures. So and then there's Plato, and then another interesting fissure area down by Plato, and the Alpine Valley, which is pretty cool looking thing. So let's go look at what we're talking about here. So these are the areas they're located at. If we scroll down a little further, you'll be able to see the areas on the map here. And then I got more of a zoom close-up thing here. So what we want to look at, and I thought what was interesting, that makes sure it's big enough to see, is like these series of fissures here that kind of seem to be radiating out. And kind of interesting to see if you can see that. You know, you can see it in the picture, but can you see it in real life or not? I think that'd be kind of cool to see that. Same with this. Here's Plato, pretty cool looking stuff. But then there's this long, looks like riverbed or something going off here. Probably another fissure or something. That's kind of look. And here's this valley, Alpine Valley, a big, like a rip in the moon or something. Anyway, I thought those kind of things are interesting. There's a lot of interesting things, but I thought I'd point those out and see if we can see them in the telescope. Question on how to use this resource. Okay. So that's what the observing session is about. Just looking at the moon is what we're focusing on in our next lab. Any questions on any of that? Okay. That covers everything. So I guess we'll see if there's any questions about anything we've covered tonight so far. Okay. How about just general questions at all? Any general questions? Okay.
I did have a quick question. I just thought about something. The difference between the meridian and the zenith is straight up, right?
Right. Yes, the zenith is straight up above you. The meridian is a line going from the north and the south. So it's a line that goes from the north pole to the south pole. Yeah. But that's a meridian, and then there's the equatorial equator. What is it called? What is it called? I don't have it open. But then there's the other one that's equivalent to the equator that goes south or east to west. I think it is. Okay. I think it is celestial equator. That's what it's called, the celestial equator. So that goes east to west, where the meridian goes north and south. Good question.
Okay.
Adeline, did you have any questions in the brief time you've been here?
Sorry, I was so late. No,
That's
I think
okay.
I really need to go back and look at the recorded session.
Yeah, do that. And I don't know if you had a chance to read through the chapters, but we cover a lot of different material this week. It's a tough week. I get so.
Yes.
Okay. All right. Well, if there's no questions, I guess we'll wrap it up tonight. So just to remind everybody, next lab is 8 o'clock at the same location that we were at last time. And bring your telescope and we'll see you there. So we'll go ahead and stop the meeting at this point. And thanks for attending, everybody.
Thanks, James.
Bye.
All right. Okay, bye.
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 Bye.